All righty. Let me give a couple of minutes for everybody to come on in, and then we'll get started. All righty. We can go ahead and get started then. So today we will continue our discussion with heat transfer methods, specifically what we started last time, which was the transfer of heat by means of conduction. And what we know about heat conduction, if you remember, is that this method is where you will have, let's say, two objects in physical contact with one another. You'll have one hotter than the other, let's say. And so the heat, the energy, will flow from the hotter object to the colder object because of that physical contact. And of course, you could think of many examples of this, but a child putting his hand on a hot stove. If you have if you put butter in a pan that's hot on the stove, the butter will melt. Well, the butter is in contact with the hot metal of the pan, things like this. It's, a very familiar way of transferring heat between two objects. And what we found was the equation we use when describing conduction is an equation which relates what's called the heat transfer rate, Q over T, which just means how much heat energy will flow per second. So Q is the amount of heat, T is the amount of time it takes for that heat to flow. And it's given by an equation, K, A, delta T over L. And so Q, again, heat energy. T is time. K, that's conductivity. That's a variable which basically describes the material we're talking about. Is this a metal plate? Is it aluminum? Then heat may flow very quickly through the aluminum. Is it a piece of glass? Maybe heat will flow at a different rate in glass. Is it a cotton shirt? It'll flow at a different rate through cotton, things like this. So this is a constant depending on which material it is we're talking about. A is the surface area, which basically means if you're trying to send heat through a material, well, the bigger the piece of material you have, the more places that heat can flow through. If you think about a window, well, the bigger the window is, the more surface area there is for the heat energy to be able to pass through the window. If you have a very small window, then there's only a little bit of space for the heat to go through. Whereas if it's a very wide window, there's a whole lot of places where the heat can flow, and so more can flow in a certain amount of time. Was there a question?
Yes, in the formula, is that an L under the change, the KA change to T?
Yeah. That's a script L. I do a script L just because a regular L may look like a 1 or something like that. Yeah, that's an L. Mhm. Delta T is the difference in temperatures. So if we have, two materials that are touching each other, one will be at one temperature, one will be at another. Another way of thinking about it is if you have, a window here or a metal plate, and you put a hot piece of metal on this side and a cold piece of metal on this side. Well, this side will be at one temperature, this side will be at another temperature. So the difference in the temperatures is the delta T. And of course, this makes sense. If there's a very, very hot side and a very cold side, then that hot side, that energy really, really wants to rush over to the cold side because the cold side is lacking energy. Whereas if the difference in temperature is very small, they're almost at the same temperature, well, there's no real pressure for that temperature, that heat energy to want to cross over to the other side. It's like, well, over there, it's just as hot as it is over here, so what's the point? So of course, a bigger difference in temperature will give rise to a faster flow rate. And then of course, the last one, L, is called the thickness. And this relates, of course, again, to the size of the object we're talking about. A thicker object, so let's say it's a glass window, and we're trying to send the heat through. Well, if you have a very thick window, then that heat has to try to work its way through the material a lot further than if it's a very thin window. Or you can also think bulletproof glass, for instance. If you shoot a bullet through a window, it's very easy if the window is very thin. But then if you have a very thick window, like they have at banks, well, that bullet can't make its way through because it's too thick. Same kind of thing here. A thicker material, the heat has to try to worm its way all the way through to the other side, and that's hard to do. So it may take longer for the heat to try to flow from one side to the other. Whereas if you have a thin piece of material, then the heat makes it through really quickly, and so the transfer of the heat can go very quickly. So that was our equation. And what we found was, generally speaking, we'll have some piece of material, temperature on one side, but different temperature on the other side. And we know information about the material, we know its conductivity, we know how big it is, and maybe we want to calculate the heat flow rate. Or another thing we may want to find out is if we wait 2 hours, how much heat will have flowed through the material. Okay, so that is to say, if you want the flow rate, then you leave it as Q over T. However, if you want the actual amount of energy that flows in a certain period of time, then you would move the T over because you now have time as a number. You put it on the other side and you solve for Q. A third option, of course, is if the question said, okay, given all this information, how long should you wait for 10,000 joules to be transferred? Well, that just means you're looking for the time. How long should you wait? So you solve for T, but now you know what Q is. You're told 10,000 joules. So now you know Q is a number. So just like all physics equations, you start with an equation solved one way. But with your power of using algebra, you're allowed to manipulate that equation to solve for one of the other variables, depending on what it is the question's asking you. Generally speaking, in this class, you'll want the flow rate, or you'll want the total amount of heat, something like that. I'm not generally going to be saying what's the surface area of the material or something. You should be able to do it, obviously, that's not a big deal. But just for your information, generally, flow rate is one of the big things to solve for, and the total amount of energy that will flow is one of the big things to solve for. So were there any questions about that, what we did last time? Well, this time what we're going to do is advance it a little bit, because we did an example last time, and that's pretty much as far as we can go with what we have so far. Now what we're going to do is modify it in a way that is slightly more realistic to the real world, and see how do we have to modify our means of actually solving the problem. And the way we're going to do it is this. Let's say what you have is two materials. You have a 3 by 2 meter wall, which is 20 centimeters thick. The conductivity of this wall is 200 joules per second Kelvin. Up against the wall is some insulation. Whose conductivity is 50 joules per second Kelvin. Let the thickness of the insulation be, let's say, 30 centimeters. If the outside temperature is, let's use 10 degrees Celsius, and the inside temperature is 30 degrees Celsius, calculate. Now I want two things here. Part A, I want to know the temperature between the materials and B, the heat flow rate through the system. All right, so that's our question. I'll draw it out a little bit. Let's say here's the wall. And then here's the insulation. And we have the inside temperature. Let's say the inside's over here. And the outside temperature is on this side. Okay. And so what's going to happen, of course, is the heat wants to flow from the hot side to the cold side. So heat will flow through the system this way, you know. And what we want to calculate is two different things. Number one, we want to know right here where the two materials touch, what is this temperature? I'll call it T3. What is the temperature in the middle? And then the other thing we want to find out is what is the heat flow rate through the material, through the system. So I want to know Q over T for the whole system. I don't want to know Q over T for just the wall or just the insulation, but pretending the wall and the insulation combined are one piece of thing, what will be the flow rate through that thing? And that's our question. So it's similar to what we did last time. You had a wall, temperature on one side, temperature on the other. You're given information about the size and the thickness and all of that. And for that question, we wanted to know the heat flow rate through the wall. Same thing here. Now we have a wall and some insulation up against each other. We know information about the size of everything and all of that. Heat will flow through the system, and we want to know the heat flow rate. Now I'm adding an extra question, which is how hot will it be in between the wall and the insulation? And we can kind of guess. If it's really hot on the left side before the wall, it's 30, and it's 10 on the other side, then probably in the middle, it's somewhere between 10 and 30. Now, what will it be? I have no idea, but it's not going to be hotter than 30, and it's not going to be colder than 10. Okay, so I have an idea of what to expect, but we still need to calculate what it is exactly. Now, how are we going to go about doing this if what we have is two different materials now? Because we have, of course, the equation Q over T is blah, blah, blah. We could do that for the wall. And then we could also do it for the insulation separately. But then how would we combine it? I mean, would we say, okay, Q over T1 is Q over T for the wall. Q over T2 is Q over T for the insulation. Do I add them? That doesn't really make sense because the heat has to go through the wall before it can get through the insulation. It's not like the wall is letting some through and the insulation is letting some other stuff through. So the total amount of stuff is you add them. That's not what's happening. What's happening is some energy has to flow through everything. So if it went through the wall, it also went through the insulation and vice versa. It can't go through the insulation unless it went through the wall. So certainly I can't just add them. And of course, subtracting doesn't make sense either. So what the heck do I do? Well, this is what we're going to have to do. Thankfully, people have thought about this before us. And so we don't have to go through the nightmare of trying to figure things out and use logic and intuition too much. The concept goes like this. Because we know that in order for heat to flow through the system, it must flow through the wall and then flow through the insulation. So no piece of energy can only go through one of the two things. No matter what, it's going to go through both. Now, say, if I look at my information here, the insulation has a very low conductivity, only 50, whereas the wall is 200. So the wall can let a whole lot of energy through, 200 joules per second, let's say. But the insulation can only let 50 joules per second through. Okay, so a way to be able to visualize this a little easier for some reason is if we think about water flowing through pipes. If what we have is a pipe, which is of a certain size, and we have a bunch of water flowing through. And let's say what we have is 200 gallons of water flowing through per second. And there's this other pipe over here, which is a lot smaller. And usually this pipe only allows 50 gallons of water to flow per second. But then I connect these two pipes together. Okay. What's going to happen? In the big pipe, of course, you were allowed to get 200 gallons per second through. But now the fact that you've constricted that pipe to a smaller pipe, which can't allow that much, let's say, well, something has to happen. One thing that could happen, let's say, is that as you start to try to flood the little pipe with the water, a lot of excess water gets built up just because it can't make it through fast enough. Okay, some of it gets through, but not as much as what's coming in. You have a big old pipe of water coming in and only a little pipe coming out. So it's possible that a lot of the water gets stuck and can't make it through as quickly as it has to. Well, if this is what happened in real life with actual pipes, then we constantly have pipes in our houses exploding. Because in reality, what you have are big pipes bringing water into your house. Those pipes diverge into different locations, your sink, your shower, your toilet, wherever. And they constrict or they get bigger, however they need to. They go up to the second floor or down to the basement, whatever the case is. Well, if every time you constrict the pipe, it's going to cause a buildup of water at the constriction, that would be a pretty big deal. But we know that doesn't happen. We can constrict pipes all the time and they don't explode. So something else must happen. So the question is, well, then what is that something else? Well, it turns out that the way things work in this universe is if you have a system like this, where you have a pipe with water flowing through at some rate, and then you constrict the pipe, what actually happens is the water will speed up in the smaller pipe than it was flowing in the bigger pipe, such that the same amount of water that flows past this part of the pipe in 1 second, let's say 200 gallons, has to flow through this part of the pipe in 1 second, the same 200 gallons. Okay. Now, how can that happen? Obviously, you have a big old pipe allowing a whole lot of water through. How can that same amount of water flow through the smaller pipe? Well, what happens is it speeds up as it tries to get through the smaller pipe. So the water running through this small pipe is moving really, really fast, whereas the water flowing through the big pipe is moving fairly slow. And the key is that it changes the velocity of the fluid such that Q over T, let's say, the flow rate on this side is the same as it is on this side. And in fact, I guarantee you, you've seen this in your ordinary life. If you've ever gone outside with a hose and you stick your thumb on the end of the hose, what happens to the stream of water? It shoots out a lot further than it was before. So usually we do that to, if we're watering plants or something and we can't reach the far plants, you kind of cover up part of the end of the hose with your thumb and it shoots the water out further. Well, the reason that happens is because once you've constricted the opening, it's like you've created a constriction in the pipe. So the water trying to get through a smaller pipe speeds up. So the water coming out of the hose will now move faster than it was before. Such that however much water was coming through the faucet originally must still be coming out the end of the hose, even though you constricted that hole. So are there any questions about this concept?
So pretty much what you're saying is that both sides are equal. It's just the velocity increases when something is narrowed down.
Yeah. So like I don't know why, but I've always found that examples with the water flowing through pipes seems to be visual for people. But if you have your hose and you turn it on, The faucet's spitting out, let's say, a gallon per minute. And you let it drain out of the end of the hose, and you see it's a stream of water coming out. And if you were to fill up gallons, water bottle gallons, then in 1 minute, without constricting it, you get a gallon of water filled up. And then you can fill another gallon in the next minute and another. Then if you constrict it by putting your thumb over the end of the hose, well, first of all, you feel the pressure hit against your thumb. That's the water trying to force its way out. The water will shoot a lot further, meaning it must be moving faster. But if you still try to fill those bottles of water, now that you've constricted it, you'd still be filling the bottles of water 1 gallon per minute. The same amount of water comes out as what was coming in, whether you constricted it or not. And the way it does it is by speeding up the fluid or slowing down the fluid, depending on if you've constricted it or expanded the pipe. And that's how fluids work. Well, it turns out heat energy works the same way. If we have these two materials here, one allows a certain amount of heat rate, another is a different amount of heat rate, generally speaking. Once we put them together as one system, then what will be true is the heat will flow through the whole system in such a way as to have the heat flow rate through the first material be the same as the heat flow rate through the second. Even though it looks like in my example, the second one is much more restrictive. So the first one should allow a lot more than the second. Once you've combined them, now each one allows the same amount per second. A secondary way, if you'd like to think about it, is once you put this yellow piece on, the very restrictive piece, it's going to slow down the first piece trying to make it through. Okay, so the first piece, hey, 200 joules per second can flow through really, really easy. But once you put that insulation on, well, now all of a sudden, 200 joules we're trying to get through, now it's stuck at the yellow piece. So it kind of makes a traffic jam, slowing down everything before it. So now, truly speaking, the first part can't make it through as fast as it wanted to. So it'll move a little slower than it was before, such that the amount of heat that flows per second in the first part will be the same as the second part. Okay. Now, if you think about it that way, it's a little different than the fluids, because what really happens in fluids is things speed up. But it doesn't matter, as long as in your mind, your conceptual view of what's going on is putting together the materials will force the heat to flow differently than it would have before. And that difference makes it so that the heat flow rate in part 1 is the same as a heat flow rate in part 2, even though if you would have had them separate, 2 different problems, you get 2 different heat rates. All right, so are there any questions about that theoretical stuff? Now, of course, what we're going to do is, now that we accept this theoretical framework, we'll show how it actually works as a mathematical thing. So mathematically speaking, what does this tell me? Well, if I have my first piece here, and then my second piece here, what do I know about them? Well, the thickness of this guy is 0.3, 30 centimeters. The thickness of this guy was 20 centimeters, 0.2. I'm told that the area of the wall is 3 by 2, which is 3 times 2 is 6. So this is an area of 6. And I'm just going to assume the insulation is the same size as the wall. So the insulation has the same area of 6. I'm told the conductivity of the insulation is 50. So K is 50 for him. And for the wall, K was 200. I'm told the temperature on the inside, which I'll call I'll call it T2, is 30 degrees. And the temperature on the outside, I'll call T1, is 10 degrees. What I'd like to find out is, number one, what's the temperature in the middle where the two things meet? I'll call that T3. And what's the total heat flow rate through the system? Those are the two things I want. Now, the way we're going to solve this problem is one method of solving it. There's the secondary method to solving these things, which in my experience has shown me students don't like the second way as much as the first way. Okay. The second way, I'll describe it. So if you want to use it, if you see it in a textbook or whatever, you're more than welcome to use it. But I'll do this one first, and this will be the way I'm going to do it for the class. It goes like this. If I want the heat flow rate through the whole system, all I have is this equation. I've got Q over T is Ka delta T over L for the first material, the wall, let's say. And then I have a different Q over T is Ka delta T over L for the second material, the insulation. I could do that. For instance, let's say I do it. Let me do it for the first material. Q over T for the wall. What is it? Well, it's K for the wall, which is 200, times A for the wall, 6, times delta T. Now remember what delta T means. Delta T means the difference in temperature on either side of the object. So when I'm looking at the object, remember, I'm only looking at the wall right now. I'm not doing the whole system. This is just for the wall by itself. Well, the wall has T2 over here on the left and T3 on his right. So I would say, okay, well, it's T2 minus T3. Now I know what T2 is. T2, of course, is 30. So I could write that in, but I don't know the value of T3. But okay, let's leave it as a variable. Maybe something will happen. And then, of course, the last piece, L, the thickness of the wall, is 0.2. And there we go. I'm kind of stuck because if you notice, there's two unknowns here. Q over T, which is the thing I'm trying to find, the heat transfer through the wall. But I also have T3 as an unknown. Well, obviously, mathematically speaking, I can't solve this right now. There's too many unknowns. So let me leave it alone. Let me look at the other guy. Maybe the other guy could give me some information. So now I'm going to do the same process, but for the insulation. So Q over T for the insulation. His K, 50.
Oh, Dr. Rossmith.
Yeah.
Is the 0.2 in meters, or what was that converted to?
Yeah, so originally it was 20 centimeters thick, and so I converted that to meters. Yeah, it's always going to be in meters. So 20 centimeters is 0.2 meters. That's right. So insulation, his K is 50. His area, also 6. His delta T, same thing. I'm looking only at the insulation and I'm saying, what's the difference in temperature between his left side and his right side? Now, one thing to be wary of here is whatever order I did for the first one, I better do the same order as the second. And what I mean by that is, if you look what I did for the wall, I did 30 minus T3. That was the left side of the wall minus the right side of the wall. Well, now that I'm on the insulation, I have to do the same thing. The left side of the insulation minus the right side of the insulation. I can't switch them. So for the insulation, it's the left side, which is T3, minus the right side, which is 10. Okay, so you could either think left minus right or right minus left, or you could think hot side minus cold side type of thing. So when I did the wall, I said, well, I know 30 is going to be the hottest part. The right side is going to be cooling off. So I'm doing hot minus cold, so I get positive numbers. So that's why I did left minus right for the wall. But since I did left minus right for the wall, I'm forced to also do left minus right for the insulation. So, okay, well, there's his delta T. And then lastly, his L, well, for him, it was 0.3 meters, 30 centimeters for him. And now again, you see we're stuck. Q over T, that's an unknown, the heat transfer rate. And T3, that's an unknown. I don't know the value of T3. It happens to be part A, the thing I'm trying to calculate. But now you see we're stuck. I can't find the heat transfer rate through either material, and I can't find the temperature in between the materials. However, because we did our math review at the beginning of the semester, hopefully everybody is thinking, well, you have two equations with two unknowns. First equation is for the wall. The two unknowns, Q over T and T3. Second equation, insulation. What are the two unknowns? Q over T and T3. Now the problem, of course, is that, is it really two unknowns or is it actually three? T3 is T3, that's just one unknown. But if you look over here on the left side, Q over T for the wall is one number for the wall. And Q over T for the insulation is some other number. So actually, this is three unknowns in reality. Because of course, if I had a wall and I did the equation on the wall by itself, I'll get some number, 250 joules per second. And then I do the insulation separately, and it's just the insulation by itself. I'll get some other number, 10 joules per second. So it's two different things. It's not the same unknown. However, the theory we just talked about when you put these two objects together, they gain the same heat transfer rate. Now I can say, actually, Q over T for the wall is the same as Q over T for the insulation because they're put together. They're not separate. So they're the same Q over T, and that saves me. Now I really do have only two unknowns. Q over T for the wall is the same as Q over T for the insulation. So that's just one thing. And T3 is the other thing. So now all I have to do, I've done the physics, is the math. Two equations, two unknowns. How do I do it? This one's easy. I don't actually have to do two equations, two unknowns. All I have to do is say, if Q over T for the wall is the same as Q over T for the insulation, then just make them equal. So what I'm about to do is say Q over T for the wall, I know is the same as Q over T for the insulation. If that's true, then I'm going to take this, which is Q over T for the wall, and put it right there. And I'm going to take this, which is Q over T for the insulation, and put it on that side. And so now I have 200 times 6 times 30 minus T3 divided by 0.2 is equal to 50 times 6 times T3 minus 10 over 0.3. So I've used the concept that the heat transfer rate through the wall is going to be the same as through the insulation because they're placed together, they're one system. And so I equated their equations. The left side is the equation for the wall, the right side is the equation for insulation. And if you look at this equation, there's only one unknown now. T3 is the only thing I need. Now, before I do it, are there any questions about that step? How did I come up with this equation?
Could you explain it again, please?
Yeah. So first thing, and I'll ask you specifically since you asked a question, but your answers are going to help everybody. The concept of the fact that when I put the two materials together, they will each have the same heat transfer rate. Does that make sense?
Yes,
That's
kind of. Sorry, no, it doesn't.
all right. So remember, like what I said with the water flowing through the pipes. If all I had was the big pipe, a whole bunch of water flows through. If all I have is a small pipe, only a small amount of water can flow through. However, when I connect the big pipe to the small pipe, what's going to happen is the way the water flows will change. And it'll change because a certain amount of water is trying to come in. It can't get through the smaller pipe normally. So what it does is it speeds up to try to force its way through the smaller pipe. And because it speeds up, that allows the same amount of water to flow through the big pipe in 1 second as through the small pipe. Because in a small pipe, yeah, it's a smaller pipe, but the water's moving faster. And in the big pipe, yeah, it's bigger, but the water's moving slower. And it works in such a way as the amount of water in the big is the same as the amount of water in the small. So does that make sense?
Yes, sir.
All right. Well, the same type of thing happens when you have two materials. We have a wall, which lets a whole lot of heat through, and we have insulation, which doesn't let a whole lot of heat through. So separately, the wall would let, let's say, 200 joules per second through, and the insulation only 50. But once I put them together, I connect them. Now the heat trying to flow through will change the way it does it in such a way as to make it so in the wall part, a certain amount of heat will flow through, and the same amount will flow through the insulation. Just like with the pipe. It doesn't work like it did before if they're separate. Once you combine them, the heat changes how it moves so that you have a whole lot of heat moving through the first and the second the same way. Well, once we accept that, now we look at this. We say, okay, let me treat the wall separately. I'll do the equation for the wall, and that's what this first equation over here is. This is just the equation for what would be the heat flow rate through the wall if it's just the wall. And in the second equation, that's how much would the heat flow rate be if it's just the insulation. And usually it'd be separate, different numbers. But then I say, actually, the wall and the insulation, I connected. And since I connected them, I know the heat transfer rate must be the same, just like with the pipe. Once I connect the big pipe to the small pipe, everything modifies so that the same amount of water flows through the whole thing. Well, instead of water, it's just heat. Same amount of heat will flow through the whole thing. All that means is the heat transfer rate, Q over T for the wall, is going to be the same as for the insulation because they're connected. Well, if they're the same, well, Q over T for the for the wall, well, that's what this thing is right here. It's just the equation for that number. So I put that on the left side. And then Q over T for the insulation, here's his equation. So I put him on the right side. And so that's how I have this final equation. Okay, so does that make more sense?
Yes, thank you.
All right, cool. Any other questions before I move on? Now, every problem we have that'll be like this, you have two different materials, you put them together, what's the heat transfer rate through the system? This is how we're going to do it. I'm going through it slowly, and particularly since this is our first time doing it. But what you're going to find is every time we have a question like this, you're going to set up the equation for the first material, set up the equation for the second material, and then equalize them. That'll give you an equation for this T3. And remember what T3 was. T3 is just randomly what's going to be the temperature in between the two materials. So now what we want to do is calculate that value. How do we calculate it? Well, this is algebra, what I have found, the easiest way to do this is nobody likes fractions, okay? So get rid of the fractions. How do I get rid of the fractions? Cross multiply the denominators. The 0.2 on the left, multiply it over to the right, and a 0.3 on the right, multiply it over to the left. And so what you have now is 0.3 times 200 times 6 times 30 minus T3 equals 0.2 times 50 times 6 times T3 minus 10. And if you don't see how I did that, here's an easier example to look at. A over B equals C over D. Okay, same thing. A is all the stuff in the numerator, I just call it A. And 0.2 is B. All the stuff on the right side numerator, I call C, and 0.3 is D. Well, all I did was
The part where the second part of the equation where you have 0.2 times 50 times 6, isn't it supposed to be 0.3 or no?
no. And I'll show you why.
Okay.
Yeah, because the 0.3 is on the denominator of the right side, when you cross multiply, it becomes the numerator on the left. And the 0.2, the denominator on the left side, when you cross multiply, it goes up to the top on the right. So if you look at A over B equals C over D, right? I want to get rid of the B. So usually you multiply by B, that cancels the B, and it brings it over here. And then of course, same, and so what you would have is A equals C over D times B. And then I want to do the same for the D. I don't like D over there in the denominator, so multiply by D, that cancels the D over here. But whatever I do on the right, I have to do on the left, so it goes over here. And so now you see we have D times A is C times B. Same thing here. This whole thing right here, I was calling A. This whole thing I was calling C. The 0.2 I was calling B, and the 0.3 I was calling D. So I have D times A is B times C. Right? That's all I did. Cross multiplied basically. The denominator on the left becomes the numerator on the right. Denominator on the right becomes numerator on the left.
Okay.
Any questions? You got it? Okay, perfect. Anybody else confused about what I did? All right, so let's finish it up. Now we're almost done because now the equation doesn't look quite as bad. 0.3, I'll just rewrite it. 200 times 6 times 30 minus T3 equals 0.2 times 50 times 6 times T3 minus 10. All right. Now what we have to do, distribute through. Okay, so on the left over here, what do we have? We've got 0.3 times 200 times 6 times 30. So I get out my calculator, 0.3 times 200 times 6 times 30. And that is, 0.3 times 200 times 6 times 30. I get 10800, the first term. But then we also have to do the second term, 0.3 times 200 times 6 times negative T3. So 0.3 times 200 times 6. And that gives me minus 360 times T3. All right, so any questions about this first, the left side terms?
How did you get the 360 if when you multiply it's going to give you the same thing as the first one?
Well, you don't get the same thing as the first one because remember, what we're doing is we're taking all of these numbers here, right? And we're multiplying them by 30, and that gives me this. And then we multiply it by this, which gives me that. Okay, so to get to 10,800, I multiplied that big parentheses thing right here by 30. And that gave me 10,800. But then the second term, I don't multiply by the 30 anymore. Now I just multiply it by the minus T3 instead. Right? Does that make sense?
Yeah, thank you.
Yeah. And a lot of times especially when you're not very comfortable with this algebra stuff. The fact that there's so many terms makes it look messy. So what you might want to do, if it's helpful, is just multiply 0.3 times 200 and times 6, and you get a number. That's equal to 360. Okay, then you could replace all of that stuff there with 360 times 30 minus T3. And that is a little bit easier to see what the heck you're doing. You don't have 4 different terms you're multiplying all together. Multiply all of these first to get 360, and then you multiply that by this parentheses over here. And it's a little bit more clear visually what you're doing. But that's how it happened. Now on the right, we do the same thing. On the right, we have 0.2 times 50 times 6 times T3. So we have 0.2 times 50 times 6 gives me 60 times T3. And in the second term, 0.2 times 50 times 6 times negative 10. And that gives me minus 600. All right, now we're nearly there. All we have to do, combine all the terms with T3 on one side and all the other terms on the other. So on the left, we'll have 10,800 plus 600, which will be 11400. And then on the right, we add 360 to the to get it to the right side. That becomes 420 T3. All right, now really almost done. Solve for T3. Divide over the 420, 11400 divided by 420 gives me 27.14 degrees. Now again, as usual, before I box this answer, does it make any sense? Well, if we remember way back to the original equation, original problem, we were told the hot side, the inside is at 30, the outside is at 10, and I'm looking for a temperature that's in between these materials. So in my mind, I'm thinking this, whatever my answer is, it better be between 10 and 30. So I look, what did I get? I got 27, that's between 10 and 30, so it makes sense. I can trust it. I'll box my answer. If this were 47, then I know, wait a second, let me go back. I must have made some mistakes somewhere because there's no way the in between these two materials is going to be hotter than the hottest part of my problem. All right, so that gives me part A. Part A, not part A. That gives me part A. Part B, we'll do it next time, but just to foreshadow it because the class is over. Just to foreshadow, now that I know T3, remember what part B is asking me. Part B says, what's the total heat transfer rate through the system? Well, we've already used something conceptually for that. We said that the heat transfer rate through the first part is the same as the second part. So for instance, if 10 joules per second flows through the first and 10 joules per second flows through the second, then it must be that the whole thing allows 10 joules per second through. So all you have to do is choose. Do I want to choose the first equation or do I want to use the second one? And it's your choice. It doesn't matter which one you choose. Do you want to look at the wall stuff or do you want to look at the insulation stuff? They both will give you the same number. So you would choose either the information for the wall or the information for the insulation. Doesn't matter. But now you know what T3 is. So right here where there's a T3 unknown, now you'll know a number there. So now you won't have two unknowns. You'll only have Q over T. And you can plug the number in and you get a value. So that's what we're going to do next time. And of course, we're going to do another example. This was only one example. We took basically the whole class to do it because we wanted to go through slowly. But we'll do another example and we'll see the same process will happen. Given multiple things in our system, we get the equation for each one individually, then we equate them because they'll both have the same Q over T. Solve that equation for T3, we now know T3. Now that we know T3, go back to either one of the other equations we had and plug the T3 in to solve for Q over T. All right, I know saying it out loud like that just sounds fairly confusing and abstract, but going through the math makes it a little more clear, I think. So again, we'll do another example next time. Also, don't forget the homework, calorimetry 2 homework, I believe is due tonight, 11:59. So if you've not already done it, it's sitting there waiting for you. Definitely get it done before the deadline. I guess that's the only other news I have. Like I said last time, the other resources are posted on Canvas for this stuff if you want to look at them. So make use of them if it's helpful. But we will continue on Wednesday. So if you have no questions, you are free to go.
I have a question towards the end of the problem.
Yes, ma'am.
So can you show how you was able, because you see how they have T3 on both sides of the equation? How
Yeah.
did you like what did you do with the other one? Like, is there a way you can fully work that out? Because I always get stuck right there.
Yeah, no problem. So are you fine at this part? 10,800 minus 360 T3 equals 60 T3 minus 600. You know how we got there?
Yeah, I seen how you got there.
Okay, so the next part, this is what I'm doing, and I'll take it step by step, because yeah, I skip steps, and that's my own fault. First thing I'm gonna do is I want all the T3 stuff on one side, okay? So what I'm gonna do is, since this one over here is negative, and we don't like negatives, I'm gonna move it to the right side. And the way I move it to the right side, of course, you add 360 T3, because when you add it to the left, it cancels the negative T3 that's on the right. I mean, that's on the left, I'm sorry. So, but if I added it there, I also have to add it on this side as well. Okay, and so when I do that, what's left is 10,800 is still sitting here. The negative 360 canceled with the plus 360 I just did. And now on the right, what we have is 60 T3 plus 360 T3 is 420 T3. And at negative 600 is still sitting over here. Okay, so does that make sense?
Yeah.
Okay, last step, or second to last step. I don't like this 600 on the right side, so I want to move it over to the left. Same thing, I add 600 to get rid of it. But because I did it there, I better add the 600 over here. And so what happens, I get 11400 on the left. And on the right, the 420 T3 is still there. And now the negative 600 and positive 600 canceled. And so that's what I'm left with. And then of course, the last step, I don't like the number in front of my T3. I want to get rid of the number. So I have to divide it over because it's multiplied right now. So if I divide it, it cancels the multiplication. But then I also have to do it over here too. And so now we have the final thing, which is T3 is 11400 divided by 420, which is what I stuck in my calculator to get 27.
So basically, even though that the T3 is separated from the 360 with parentheses, you still remove those together, because that's why I will only like add the 360 and leave the T3 still.
So you over here for this step right here.
Yeah, that step right there.
Yeah. So think about it like this. Let's say we have 10 plus 2x equals 4x plus 5. Okay. Let me move the 5 over first. So if I subtract 5 over here, I subtract 5 over here, and I get 5 plus 2x equals 4x. Well, I want to get all the x's on one side. So this is 2x, and I'm adding 2x. So to cancel that out, I subtract 2x. So if I'm adding 2x and I subtract 2x, those things cancel out completely. But because I did it on the left, I have to do it on the right as well. And so now I have 5 on the right, and I have 4x minus 2x is 2x. You see? And that's basically what I did with the T3 stuff. It's just bigger numbers sitting there, so it makes it look a lot messier. This is a little cleaner because it's smaller numbers. If you have some number times your variable, and you want to move the variable over, move the number with the variable first. Collect all the numbers with variables all together. Then at the very end, that's when you get rid of the number that's in front of the variable. Okay, so what I didn't want to do is just move the x over here and leave the 2. You can't do that. That's illegal. What you can do is move the whole thing over and combine it with the whole thing over here. And then after you've done all of that manipulation, on the very last step, where you only have one term with x in it, that's when you can move the number over and leave the variable alone. Okay?
Yeah, but see, what I was, because the 320, 360, I forgot what it was. Since it was separated into parentheses, I seen them as being two separate things. So I didn't have them
Oh,
to where
yeah,
they're
yeah.
together. You see how
That's-
with 2x is together, but with 360
Yeah.
is separate.
Right. That's just a way of notation. What I always try, especially like with 2x, it's easy. But if it's 202x, that starts to look a little messy. So what people usually do is just put parentheses. So it's still, 2x and 2x is the same thing. It means 2 times x. Yeah, so don't let that parentheses with the number in front of the variable confuse you. It's the same thing as just writing it without the parentheses. It's just to let you know you're multiplying x by this number. And it's supposed to make it look cleaner in your equations. So it doesn't mean anything different. It's just like 2x without the parentheses.
Okay. Thank you so much for helping me with that.
No problem. No problem. See you later.
See you later.